Hello, I'm Fengchen Gong. Today, I'm going to tell you how we can zoom into network data like we zoom into images. Network management includes various critical tasks, such as debugging network incidents, detecting attacks, and planning the network. All these tasks rely on monitoring data collected on network devices in data plane. Because the performance of the tasks rely on the quality of the monitoring data, we typically expect network monitoring to be general, cost-efficient, and of fine granularity. General means we can collect multiple signals altogether in a straightforward way. Cost-efficient means we can do this on just commodity hardware. Fine granularity means monitoring data should capture short timescale events. However, as networks and workload scale, it's becoming more challenging to collect, store, and processing fine-grained monitoring data because of the hardware constraints and storage limitations. Therefore, oftentimes, people are just presented with sampled data, which is coarse-grained and unreliable. There are some existing work that try to solve this, but it's hard to satisfy three requirements at the same time. Let's see some practices. Mirroring traffic from routers to collectors can satisfy generality and fine granularity because they allow operators to do any customized queries at any granularity. But mirroring requires expensive and customized hardware for the significant bandwidth and processing. Sketching and other probabilistic data structures can collect fine-grained telemetry in cost-efficient way, but they are designed for specific per-flow tasks, such as identifying heavy hitters. Generalizing them to other tasks is not straightforward. Network tomography can infer unmeasured metrics from the measured ones, but it only works on linear relations between signals and non-network topology. It is hard to generalize as well. Sampling, as I mentioned before, is the most accessible tool for operators, but it is coarse-grained. Our vision is to add a layer on top of the coarse-grained monitoring data, which recovers the fine-grained monitoring data from the coarse-grained ones. More specifically, consider a network system that is described by a set of fine-grained time series. A monitoring infrastructure senses the system by applying some sampling functions and outputs coarse-grained time series. Given the coarse-grained time series, the goal is to impute an approximated fine-grained time series, and then they can be used as input to different downstream tasks. This is a practical framework for network monitoring that satisfies the three requirements. It is a pure software solution without hardware change. It can be applied to different signals as long as they are cross-correlated. It can increase granularity of time series by up to 50x. Our problem is actually analogous to the problem in image superresolution, which relies on pixel correlations. I know some of you might have some doubts, and you're thinking, how could this ever work? You might also be thinking about some cases or examples that this wouldn't work. Let's go over one example together. The plot shows the queue length of two queues. Q1 is a bursty queue, and Q2 is a consistently long queue. These two queues look very different. However, if we apply the sampling function on the queue length, which is taking maximum over 50 milliseconds, they are actually very similar, exactly the same. Looking at this example where coarse-grained versions are the same, it seems impossible to impute or recover the correct fine-grained version, right? However, if we look at auxiliary signals, such as packet drop and packet send, two queues are very different even at coarse granularity. Indeed, packet drops will be higher for the long-standing queue compared to the bursted queue. Therefore, we can use the correlations between different signals to impute the correct fine-grained time series. Going back to our question, why would this ever work? The answer is, we can leverage correlations among network time series to recover what's being missing when we do sampling. This correlation will also impose constraints on what the fine-grained time series should look like. Next, let's see how the system is designed around this idea. Although the correlations seemed obvious, it can be very complex to model them as explicit expressions. So we ask machine learning to help us discern the correlations automatically. We use a model called transformer. It is a typical model in processing sequences of words in natural language processing. It uses attention mechanism to find out how each word in a sequence relates to all the others. Here, we replace words by time series data. And then to output the fine-grained time series, we add linear layer on top of encoder. A strawman approach will look like this. We use a small set of data to train the transformer. And then during inference, transformer takes a new coarse-grained time series, possibly from production, and impute or output its fine-grained version. However, this strawman approach does not work. Let's see why. The first problem is the imputed time series is inconsistent and incorrect. Here, we show the red square is the maximum queue length over 50 milliseconds, which is also our coarse-grained input. What the queue length should look like, the ground truth is shown here. Its maximum is exactly in the input to the strawman solution. However, what strawman gives us is the orange line, which is embarrassingly wrong. It does not reach to the maximum. There is a critical need that we should incorporate knowledge into what the transformer is doing right now. To do that, we first categorize knowledge into measurement and operational knowledge. Measurement knowledge means if we apply the sampling functions on our imputed fine-grained time series, we should get the coarse-grained measurements back. Operational knowledge captures the correlations between signals based on the algorithms that we use in networking. For example, the queue length should not be more than the dynamically allocated threshold. We represent these knowledge as equality and inequality constraints. And then we incorporate constraints into the loss function to teach the transformer to output consistent time series. Specifically, we add the constraint violations into the loss function as regularization terms. To better train the model using this loss function, we adopted the augmented Lagrangian method, which introduces this lambda as weights. Lambda is updated using the constraint violations of the ML output. That means when the constraint violation is higher, the weight will also become higher. This leads to a more effective minimization. And through multiple iterations, the transformer will learn to minimize constraint violations. Incorporating constraints into loss function does not guarantee constraint satisfaction. So we introduce the constraint enforcement module to further correct ML output. Inside of it, we use integer linear programming. The variables are the imputed fine-grained time series. Constraints are what we defined before, equality and inequality constraints. The objective is to minimize the total difference between the original transformer output and the corrected output. Although correlations can help us impute fine-grained time series and help dispute some of the ambiguity in coarse-grained data, it's actually not always the case, and it's not enough. Let's see another example. Here, the two fine-grained cues are different because bursts occur at different times, but their coarse-grained measurements are almost identical. This is the scenarios when the coarse-grained measurements are too coarse-grained so that similar input can correspond to different output, fine-grained output. To solve this, we want to refine a small set of training data where these cases exist. Specifically, for the similar cases, we collect all the plausible output and form a single set. And then we will refine the similar cases to have the same set of plausible output. Then the transformer will learn from all the plausible output and then learn the correlations accordingly. End-to-end workload looks like this. The training data is being refined first and then used to train a transformer with knowledge augmented loss. And then during inference, transformer takes a new coarse-grained time series and then impute a fine-grained time series being corrected by constraints enforcement module, and then the output is used by downstream tasks. We evaluate Zoom2Net in different management tasks using public dataset. The public data we use is for fine-grained ground truth. We manually sample them to form the coarse-grained measurements. We want to find out how accurate Zoom2Net imputed time series is to ground truth and how useful the imputed time series is in performing downstream tasks. We compare with KNN, coarse-grained time series, plane transformer, and another imputation model called BRIDS. We have several case studies in the paper, and here we only present one. This case study imputes 1 millisecond link utilization from 50 millisecond coarse-grained measurements. The data comes from Meta. For imputation accuracy, we want to look at 4 different metrics: MSE and Earth mover's distance, which is distribution difference, autocorrelation, and 99th percentile. We report normalized relative error to ground truth. Zoom2Net achieves the lowest error, which is 33 to 53% better accuracy than baselines. Then we apply burst detection on Zoom2Net imputed time series and analyze burst height, burst duration, and burst volume. We show that Zoom2Net improves downstream tasks by an average of 38% compared to other baselines. We further did an analysis on zoom-in factor. We changed the coarse granularity of the input to different numbers, 25 millisecond, 50, or 100 millisecond, to recover the same 1 millisecond fine-grained time series. We show that Zoom2Net's imputation accuracy and downstream task performance only degrade by an average of 0.4% and 7% when we increase the zoom-in factor from 50x to 100x. In conclusion, we show that it's feasible to impute fine-grained time series from the coarse-grained versions. Zoom2Net does that by leveraging machine learning to learn correlations and formal methods to ensure consistency. Zoom2Net demonstrates improvements on downstream tasks performance. Thank you.